it's my pleasure to introduce the first speaker for AGNES. Kristin Lauter is a number theorist and cryptographer at Microsoft Research. In fact, she's a research manager of her group at Microsoft Research. I've known Kristin for quite a long time, and we've worked together on many projects. One thing I would like to mention is that Kristin is currently the president of the Association for Women in Mathematics, and so she's been active in a number of areas that are important to mathematicians. If you haven't had a chance to take a look at the AWM website and see all the things that are going on in terms of research conferences and symposia, please do. Anyway, it's my pleasure to introduce Kristin and welcome her to AGNES and to Graph.
Thank you. So with that kind introduction, I feel that I have to return the favor. I tried to turn it on. Is it on now? It's got a green light. Yep, it's on. So Jill was my first year professor, undergrad at the University of Chicago, so largely responsible for me going into mathematics. So, and she was also president of the AWM several years ago. So I want to start by thanking the organizers for inviting me. It's a great opportunity to be here to talk to you. I prepared a talk which I hope will be of general interest to a fairly broad audience of mostly algebraic geometers. But I was told in particular that there would be a lot of graduate students in algebraic geometry. So I thought I would take this opportunity to talk about a lot of open problems. And that brought me up to my first problem, my title. So I came up with this title, Cryptography Problems in Algebraic Geometry. But then I was like, or is it algebraic geometry problems in cryptography? And then I actually started to think, what's the difference between these two things? And the interesting thing is that I think there is probably a subtle difference in the following sense. So cryptographic problems in cryptography, are often kind of very algorithmic in nature, and I'll talk about that in a little bit more detail. Whereas often in algebraic geometry, I think, in mathematics, people often think about that doing math means just kind of proving a theorem. So the interesting thing is, and the point I'd like to make through a lot of examples today, is that when you're doing research in this area, this is kind of a distinct research area, which is a combination of cryptography and algebraic geometry, I think you really end up doing both. There are algorithmic problems that need to be solved, but then a lot of times to solve algorithmic problems, you have theoretical problems and theorems that need to be proved as well. So I think both titles are appropriate. So basically, I don't know how much I'm going to get through in an hour, but I decided to list a bunch of kind of 9 open problems areas. These are all problems I listed because I really feel like there's still some significant kind of open component to it. There's some partial solutions that I'm going to talk about, but there are some very interesting challenges, some of which would have a very, very big impact on cryptography and the way that it's practiced today. So with the exception, as you can probably tell from the length of the list, I'm not going to be able to go through all of these problems. And roughly speaking, the amount of detail is going to decrease as we go from problem to problem. And I'm probably going to end somewhere around just telling you what problem number 5 is. So most of these I really won't have time to talk about. I can say a few words about them at the end if there's time. But so besides the kind of a little bit of a cryptography preamble that I'm going to do, there's going to be kind of 4 main sections. So if you're not as interested in one problem or you don't follow one problem, you can wait until the next and you might find it more interesting because some of them are quite a different nature. So kind of my comment, my view on this area as a research field is that, like I said, so cryptography problems are mostly algorithmic. That is, you're usually thinking about, okay, well, if I pose this problem and I say it's hard, how long is it going to take an attacker to solve this problem? Another thing that's extremely important is, if I want to go tell my management that we should implement some new crypto system, what's the overhead going to be? How many seconds or milliseconds or microseconds delay is a user going to experience when I all of a sudden layer security on top of whatever protocol they were trying to do? How much space is my code going to take up if it's going to run on some constrained device? Is there enough memory on this device for this code to run? Things like that. How expensive is it going to be for an attacker to mount an attack? How much hardware and space are they going to need for this algorithm? That kind of thing. So a lot of these are results that, so if you have a solution, an algorithm, it's usually measured not just by the fact that it exists, but how good is it in the sense of what is its running time and also what are its space requirements. So that's the kind of framework for research in this area. And a very key set of terminology, and you'll probably hear me mention this throughout the talk, we talk about polynomial time algorithms versus exponential algorithms, and then kind of in between sub-exponential algorithms. So what we mean by polynomial time algorithms is that their running time, or it could be applied to space as well, but their running time is a polynomial in the input size. So the input size is the number of bits it takes you to write down the input. So if it's a group of size, we usually talk about the order of G, then a polynomial time algorithm would be something that runs in time a polynomial in the log of the size of G, of the group order of G. So one thing that you'll hear me mention quite a few times is square root algorithms. Square root algorithms are algorithms that run in the square root of the group size. So those are exponential algorithms. They are not polynomial in the log of the group size. And in between exponential and polynomial is sub-exponential, which are essentially you can think of them as they're exponential in some kind of fractional power of the log. So that's kind of an important framework for considering these. So the other thing that's kind of interesting about this area, it's a really awesome area to do research in, but it does require this kind of strange combination of backgrounds. So algebraic geometry and number theory figure heavily into it. You'll see that in a lot of different aspects of the problems I'm going to mention today. But you also really need to have a good sense of algorithms because cryptographic sizes are very, very large. They're much larger than what you're used to thinking about when you think about math problems. And so you really have to think about algorithms in this sense that I talked about above that considers their running time and their space requirements. And also another aspect of this research area, and I think this may be becoming more and more true in lots of areas of math, but definitely programming ability is very, very helpful. And being comfortable and really having fun with programming is kind of a requirement because you really need to be able to compute things, experiment, see how long things take to run, things like that. So just one last point, I thought this was just kind of a fun thing to mention. It's also an area that to a large extent you can actually teach to computer science students with very little math background. So I taught a graduate CS course on elliptic curve cryptography to CS students who knew very little more than what a finite field was. That was pretty much all they knew. And I'm not sure, but I think they enjoyed the class. I picked up a couple of interns from that class, so at least some of them enjoyed it. Okay, so I'm going to start with a couple of minutes of just a little bit of an overview of cryptography. I know that some people probably know quite a bit about it, but just to kind of set the stage, cryptography, people say, oh, the art of keeping secrets. But that's actually only a part of it, right? So cryptography has several main key components. This isn't totally exhaustive, but this gives you a very good idea of the flavor. Cryptography encompasses key exchange, which is two parties trying to agree on a secret, exchanging only public, only information exchanged in public. Signature schemes help assure kind of authenticity. So signature schemes allow parties to authenticate themselves, and encryption actually preserves secrets, kind of preserves confidentiality of data. And some examples of public key crypto systems that many of you will be familiar with are like RSA, which was proposed around 1975. So that's based on the hardness of factoring large integers. And just so you know, so there are sub-exponential algorithms which are known for breaking RSA. And that means that the key sizes that we have to use are much larger than before there were sub-exponential algorithms that were known. So the main sub-exponential algorithm that's known, that's used for breaking like RSA moduli, is called the number field sieve, and it uses a lot of interesting number theory and number fields algorithms. So Diffie-Hellman, I'm going to tell you a little bit more detail about what Diffie-Hellman is. Diffie-Hellman is a protocol for key exchange. And then there are elliptic curve versions of these things. Elliptic curve Diffie-Hellman. DSA is a government standardized signature algorithm, and then there's an elliptic curve version of that algorithm. So just very briefly, in your day-to-day life, you will be using and experiencing these crypto systems at least in the following ways. So key exchange is used to establish secure browser sessions. So whenever you go to an HTTPS site, which is more and more often, there's lots of sites that are HTTPS. So signed encrypted email is not something that actually most of us use. Most of us use like Gmail or Hotmail or something like that, which is not signed and not encrypted. It's like sending a postcard, which is kind of unauthenticated. But for some kind of, let's say, internal corporate mail or things like that, people could implement signed and encrypted email. And that's governed by the standard S-MIME. So virtual private networking is what's used to connect, like when I want to connect to the Microsoft corporate network, and that's governed by the standard IPsec. And then authentication is very important, but it's kind of hidden to all of us, is that, sometimes you'll go to a website and it says, oh, the certificate for this website is not recognized. Are you sure you want to go there? And then usually you say, yes, I want to go there anyway. But so the point is that what's happening there is that most of us, like in the US, we will kind of there's a chain of trust. And we'll kind of chain up to well-known or recognized certificates. And so like either if you're traveling or if somebody's kind of established their website independently or something like that, and not maybe in a mainstream commercial setting, they might not be chaining up to the same root of trust that we recognize. So underneath all of our e-commerce and our trust, there's a very interesting kind of public policy question there, which is, like kind of who should be trusted to issue certificates on public keys. And so right now, we're just all kind of taking this for granted that this works and that there's a public key infrastructure that's actually deployed by companies. So VeriSign, for example, deploys these. So although many people may be well aware of and familiar with key exchange, I'd just like to say what it is in the kind of the mathematical sense. So two parties, Alice and Bob, want to agree on a secret key, and they're going to exchange information, and we can assume that there's an eavesdropper, Eve, who might see this information. So that's why we say it's kind of publicly exchanged. And Alice is going to pick a random element A that she will keep secret, so the red is secret. Bob picks B. But what is known is some group. Some group is publicly known. Think of it like a phone book or some protocol that's been published so everybody knows what group you're going to work in. In particular, sorry, the PowerPoint just capitalized my group generator. It was supposed to be a little g. Little g generates this group. So in general, you could work, for this, we're going to work in an abelian group, and it wouldn't have to be cyclic, but we would, if not, we would work in some cyclic subgroup. And it might introduce some extra checks and issues that would be problematic. So we're going to assume that it's a cyclic group generated by little g for now. And then Alice is going to send g to the A and over to Bob. And Bob is going to send g to the B over to Alice. And then the secret is going to be established as g to the AB. So I'm writing this, it's a little bit odd because I'm going to spend most of the talk talking about elliptic curve cryptography, where the group law is additive, it's an addition law. But ironically, in computer science, the computer scientists always write groups multiplicatively because they were used to Diffie-Hellman in like Z mod PZ star or FP star. And so everybody thinks of like all the protocols as being the multiplicative group law. So they're all written like this, even if we're gonna, in the end, we're gonna work in a group where we would prefer to write the group law additively. So the point about this secret is that g to the AB is something that both parties can compute given the publicly exchanged information in their own secret, because each one can take what they receive and raise it to their own power. Whereas anyone in the middle, all they know is g to the A and g to the B, and we should all know that putting those two together will give us g to the A plus B, not g to the A times B. So that's where the secret comes from. And there's actually a problem which I haven't written down on the slide, which is called the Diffie-Hellman problem, that explicitly states the hardness of breaking this protocol. Diffie-Hellman problem is, given g to the A and g to the B, this public information, can you compute g to the AB? And that's called computational Diffie-Hellman. And then there's a decision version of that problem, which is DDH, decision Diffie-Hellman, which is given given three group elements, which is basically g to the A, g to the B, and then g to the Y, just decide whether g to the Y is equal to g to the AB or not. So there are some groups in which this decision problem is still unknown to be solved, but there are groups in which the decision problem is actually easy, whereas the computational problem is still hard or still unknown. So one of the practical issues, like I said, the computer scientists were used to working in Z mod PZ star as a group. That's a nice, cyclic group. Or the problem, so what I mentioned in the beginning that there were sub-exponential algorithms known for RSA. At some point, there were sub-exponential algorithms that were discovered for working on the discrete logarithm problem in Z mod PZ star. And those are called index calculus algorithms. And very, very beautiful set of ideas. And those sub-exponential algorithms caused the group size, the size of P to have to be increased dramatically. So today, like a minimum government standard size for P, if you want to work in Z mod PZ star, would be like somewhere around 2,000 bits. So 2048-bit Diffie-Hellman is usually like the minimum size. And so then when you think about doing computer arithmetic, if you have computers with word size, 32 bits or 64 bits, and you have to do multiplication mod P, where P is 2,048 bits, the computational cost of these things can be pretty significant. And also just even the size, these keys get to be kind of long, 2048 bits. So that introduces issues of power, bandwidth, time, all of these things. So at some point, an alternative to working in Z mod PZ star was introduced, and that was based on the group of points on an elliptic curve. So this has given rise to a kind of a whole field called elliptic curve cryptography. So like I said, RSA was introduced around 1975. Elliptic curve crypto was introduced around 1985 independently by Neil Koblitz and Victor Miller. And there were a lot of, for those of you that were not around at that time, my understanding is that there were a lot of really great number theory algorithms kind of being proposed and investigated around that time in the mid-'80s. So that includes things like the first polynomial time algorithm for point counting on elliptic curves by René Scoof, the proposal for the elliptic curve factoring method from Hendrik Lenstra. And so apparently there were just a lot of really great algorithms based on elliptic curves that were kind of being proposed and investigated at that time. And so it was kind of nice and possibly natural that it actually came from two different people in that community, this proposal of having elliptic curve cryptography. So the security of elliptic curve cryptography is based on this hard problem, which is related to the Diffie-Hellman problem. I'll say a little bit more about that in a minute. But just to say a couple of words about this kind of research community. So the 25th anniversary of ECC was actually held at Microsoft Research in 2010. We sponsored that. And just to give you an idea, there were about 125 researchers there worldwide, and that includes people from academia, government, and industry. So it's a very multidisciplinary community, and it's larger than you might think. I mean, there's quite a few very, very active researchers and lots and lots and lots of papers published every year. And actually just this week in Bordeaux is the 30th anniversary of ECC, and they hosted ECC there. and I was told that there were about 150 researchers there. And this community also includes a lot of people that work on what's not just elliptic curve cryptography, but some of the generalizations that I'll talk about today to Jacobians on higher genus curves, and also things like pairing-based cryptography, which are also based on pairings in algebraic geometry. So pairing-based cryptography allows us to do a lot more kind of new and interesting protocols than what we could do without the pairings that we get, like the Weil pairing and the Tate pairing from algebraic geometry. So what is this? So this is the first problem on my list. So I'm not doing so well because I took up 20 minutes and I haven't even started on my first problem yet. So the first problem is kind of the biggest in the sense. It's the elliptic curve discrete logarithm problem, ECDLP. And this is very, very important because, well, so I've been at Microsoft for around more than 16 years. And when I first went there, I started working on getting them to ship elliptic curve cryptography. And after about 5 years of working on things, so we finally started shipping elliptic curve cryptography around 2005, and Vista was our first product. And now pretty much all of our products have elliptic curve cryptography in them, and it's worldwide kind of industry standard. So if you break ECDLP, that's going to be a big deal. So this is definitely the #1 problem on my list. This is a big problem. And so what do we mean by break? Again, what we have generic algorithms for a lot of crypto problems which run in the square root of the group size. And so typically when people say you break something, it means you come up with an algorithm that runs in less than the square root of the group size. And sometimes that doesn't have a big impact in practice if it's only slightly less, but certainly it would have it has an impact over time in choosing key sizes and trying to see the future of how you should set parameters for crypto. So in general, like if you can find a sub-exponential algorithm, that's what really kind of breaks things. It makes it very kind of unwise and impractical to implement something once you know that there's sub-exponential attacks. So when I said I'm a little bit lying here. It's not the best known algorithms are running in the square root of the group size. In general, for these kind of like the Diffie-Hellman problems and some other problems, they're actually running in the square root of the largest prime factor of the group size. This is kind of an important point. Because if you have a group which has smooth order, you have this kind of Pauling-Hellman approach, which allows you to break up like a discrete logarithm problem into into pieces and basically use kind of like a Chinese remainder theorem approach to solve the problem in the whole group. Okay, so sorry, I said discrete logarithm problem, but I didn't state the problem. The problem I stated the Diffie-Hellman problem. Now the discrete logarithm problem is, let's say you're given a generator for a group, so call this generator little g, and if you're given g, you know g, that's public, and then you see another public value, g to the b, can you find b? That's this discrete logarithm problem. And clearly if you can solve the discrete logarithm problem, you can solve the Diffie-Hellman problem. But interestingly, the reverse is not obviously true, and there is a reduction in the reverse direction that, interestingly, involves elliptic curves that works for black box groups, but which is not known in general to be true. So a couple of kind of extra points. I'm just going to say a couple more words about the history of the discrete logarithm problem for elliptic curves. So like I said, this was kind of introduced in 1985, and so except for, as part of the reason that it's an industry standard now, except for special cases like supersingular elliptic curves, we don't know any sub-exponential attacks. So what is this business? What happened for supersingular elliptic curves? This is pretty interesting. So supersingular elliptic curves were proposed early on to be used because it could get some efficiency improvements for implementing the system. And then the Menezes-Okamoto-Vanstone attack came along, and you basically used pairings on elliptic curves, like the Weil pairing on an elliptic curve, to show that you could attack supersingular elliptic curves, and that made those particular curves, completely unacceptable for implementation of elliptic curve cryptography. But with the exception of supersingular elliptic curves, we really don't have any generic attacks on elliptic curve cryptography, which is why I stated it as kind of my first open problem.
But what is the public information in the case of?
So for an elliptic curve I kind of took these slides out, but so the public information would be the actual curve. So if we ignore characteristics 2 and 3, you can put an elliptic curve in a short Weierstrass form like this. So the public information would be the field that this curve is going to be defined over, so some prime P. And then these two elements here, A and B. A is often taken to be -3, just for efficiency reasons. And so it's essentially this element here. And then there needs to be, so let's suppose the group order over this prime field FP. Let's suppose the group order is prime. Let's say it has order Q. Then you also need a point on the curve to be specified. That's your generator for your group. And if the curve has prime order, then you can basically take any point, but in particular, everybody needs to agree on the same point. So if you look up like the NIST standards for elliptic curves, you will find a list of elliptic curves, each one specified like that with a point, which is its generator, and they'll have different types of curves at each security level. So right now, that's why I put this 256. You'll have curves which are called P256 curves, which means they're over prime fields of 256 bits. And there's both prime fields and there's what are called Koblitz curves and binary curves. So there's also curves in characteristic 2. I'm not going to talk about the characteristic 2 case that much. But then there's currently in the NIST standard, there's curves going up to security level, like 256-bit security level, which means 512-bit field. So actually, I could talk lots and lots about standards for elliptic curves, but in the interest of moving on, I'm not going to say more about that, but if anyone wants to know more about that, you'd be welcome to talk to me later. Okay, so how does elliptic curve cryptography work? There has to be a group law. What is the group? The group is a group of points on an elliptic curve, which many of you with an algebraic geometry background will not only be familiar with, but probably know lots more fancy definitions of elliptic curves than this. But for our purposes, it just means the group of points on this affine model for the curve, along with the point at infinity. And there's a group law, which is always kind of shown with this picture, where if you have 2 points, Q1 and Q2, that you want to add together, you pass a line through them. You look for the third point of intersection with the curve. This is supposed to be a cubic, even though my graph is a little bit pathetic. It might not actually be a very good cubic. And then, so in a cubic, you would expect a third point of intersection with this line. And then you pass a vertical line through there. And the sum of Q1 and Q2 is minus R1. So an important point in this picture is that from an algebraic geometry point of view, what's happening is that there's a group here, which is basically degree 0 divisors modulo principal divisors. And principal divisors are the divisors of functions on curves or varieties. And so here's a function. It's a line. And so the divisor of this function on this curve is just these 3 points. So what it's saying is these 3 points added together in this group, like think of it as a formal sum, is 0. So that's why Q1 plus Q2 is actually minus R1, because the sum of these 3 things is 0. And we'll see why in a few minutes why that's kind of interesting in a larger context. Okay, so just to summarize, this is kind of all I was going to say about the elliptic curve discrete logarithm problem. This is kind of the foundation of the talk, because this is the fundamental problem. And a lot of these other things that I'm going to talk about are very related to this, the kind of the practice of elliptic curve cryptography, which is based on the hardness of this problem. So here's an interesting, so see, I changed the color scheme so that you could see that this was the next section of the talk. And also because maybe everybody's not as in love with purple as I am, so we went to white for now. Okay, so here's another group that you could use in cryptography. And in a few minutes, I'll tell you why you might want to use this in cryptography instead of elliptic curves. So this was introduced by Neil Koblitz a few years after ECC, and it was around 1989, introduced the idea of using the Jacobian of a hyperelliptic curve for crypto systems instead of just using elliptic curves. And a hyperelliptic curve, in particular in genus 2, we're going to think of as being given by an affine model y squared equals f of x, where f has degree 5 or 6. And the elements of the Jacobian will be represented by pairs of points on the curve. So if you're an algebraic geometer, you might know this from thinking of the Jacobian as being like a symmetric product of the curve with itself, g times. But you'll also be able to see it kind of from our description of the group law that I'm going to give in a few minutes, why this works out nicely. So, and there's also a couple of important things I'll come back to, the Mumford representation and the group law for Jacobians of hyperelliptic curves. So here's some kind of rough pictures again. On the left-hand side, an elliptic curve, right-hand side, a genus 2 curve. Again, we're drawing these curves kind of like over the real numbers, whereas in cryptography, we're actually going to be implementing these things over a finite field. But the algebraic rules that we give for implementing these group laws will also work over FP. So you might say, okay, well, why would you want to move from this curve to this curve? So if you use the Hasse-Weil theorem, you'll see that over FP, the number of points on both curves is going to be in this region, right? P plus 1 plus or minus 2g times square root of p. So you're thinking, oh, they both have roughly p points, right? P plus or minus, some multiple of square root of p. So why would you want to move from one to the other? Well, and also because if you look at your nice group law on elliptic curves, which has this, chord, they call it a chord and tangent method, where you take a kind of chord through these points, or if it's a doubling operation, you take a tangent, And so if you look over on the genus 2 curve, well, this doesn't work very well, right? You take a line, you pass it through there, and you don't get one other point of intersection. So that's not working very well either. So, but the nice thing is that if you look at the number of points in the group that you're going to be interested in, the number of points on an elliptic curve will be around p, whereas the number of points on the Jacobian will be around p squared. So what this means is for the same group size, you can cut the field size in half. And so there's actually this interesting tension, which is still, we're kind of right on the cusp of being able to make use of this really in practice, which is that if you think about computers, they were 32-bit words, now we're 64-bit words, are we going to be 128-bit words, mainstream anytime soon? Well, once you can fit a field element inside a single word on the computer, you get massive efficiency improvements. So if you think about cutting the group size in half, the field size in half, you are definitely getting a major efficiency improvement for your operations, and potentially like this kind of idea of getting, if you make the genus high enough that you get every field element in one word in the finite field is very tantalizing. So there's this motivation, if we go from genus 1 to genus 2, we can decrease the size of our field. That's very good. We get efficiency improvement. So, but then what happens to our group law? Our group law gets kind of more complicated, right? So the simple idea of passing a line doesn't work anymore, but this other idea does work. So I'm just warning you here, this is my favorite picture in the whole world. I used to have this on my office door. I usually, every talk, try to find some excuse to show this picture. So this is a picture of the group law in genus 2. And the interesting thing is that, so I introduced this picture in a paper in around 2001. And I basically got it from the Cassels-Flynn book. So I don't know how many of you know Cassels-Flynn book on genus 2 curves. In the end of that book, they have a description of the group law. And they basically tell you this is the group law. What do you do on genus 2? Divisors, or in the group, or group elements for the Jacobian are pairs of points. So if you have P1, P2, that's a group element. And if you want to write it as a degree 0 divisor, you need to write like P1 plus P2 minus 2P infinity so that it actually has degree 0. But usually you just kind of forget about that and think about it as being represented. This is like the Mumford representation represents these 2 points as a quadratic polynomial, actually. So we have these two kind of divisors represented by these 2 pairs of red dots. So now how do we add them together? Well, again, the same philosophy of what the group law is. You want to have a principal divisor. In other words, the divisor of some function. So you want a function that passes through these 4 points. So you take these 4 points, you figure out a cubic function, and then you pass through those 4 points. And then generically, like over an algebraically closed field, you expect it to intersect this. So this can be written as a quintic or a sextic. Oftentimes we think of, like, we use a rational point to make it into a quintic, but you can just think of this as a sextic. And so generically you expect 2 other points of intersection with this curve. And so just like in the elliptic curve case, this divisor is supposed to be 0. So this plus this plus this is supposed to be 0. So this should be, minus this should be equal to these guys. So you take these 4, you kind of formally add them together, but now you want to reduce it. So this is like this very nice reduction algorithm that we have for hyperelliptic curves. But it's actually not known in general for algebraic curves. That's another thing I could have put on my list, is unique kind of reductions for other types of curves. So these 2 points, this is minus these guys, so you need to kind of flip these over the x-axis. So R1 plus R2 are the sum of these guys. Okay, so this is my view of the group law of a genus 2 curve. So, but I come along and I start working for Microsoft, and I find out that people in cryptography do not think this is the group law on a Jacobian. What do they think is the group law? They think Cantor's algorithm is the group law. So interestingly, Cantor, I heard he was very influenced by Hendrik Lenstra and René Scholf in developing this algorithm. He thinks of a genus 2 curve as basically thinking of it as its function field representation. So think of a hyperelliptic curve as being a degree 2 extension of or like a degree 2 cover of the projective line. So think of that as being like the analog of a quadratic extension in number fields. Okay, so here's the number field world and here's the function field world. And over here in number fields, we have this really nice group law in quadratic fields that we've known for a long time, which is Gauss composition. So basically, if you take Gauss composition for like ideal class group of quadratic number fields and kind of push it over to function fields, you get Cantor's algorithm. So Cantor's algorithm takes kind of divisors and represented in terms of like Mumford's notation and does this reduction and it basically does composition and reduction and all of this. So, but since that wasn't what I thought the genus 2 group law was, so I wrote a small paper showing that these 2 things are equivalent. And ever since then, I've been showing this picture to everyone so everybody can kind of see the group law instead of just compute it using Cantor. So,
why are there only 6 points of intersection? Shouldn't there be 15?
well, so this is pretty, this is using the affine. So think of it as y squared equals f of x, where f generically has degree 6. And then this cubic that I've drawn, this is basically y equals, say, h of x, where h has degree 3. So now I'm going to plug in h in for y, and I'm going to square it. And so we've got something in x, which is degree 6. So over an algebraic closure, we're getting 6 solutions. So you were thinking of trying to use like Bazoo or something.
Yeah.
Okay, so now that I've tried to convince you that genus 2 curves are interesting for cryptography, I'm going to tell you about the second problem, which is very interesting and quite important, and that is, so how do you actually generate safe curves for crypto? So somebody earlier asked, well, what's the public information for one of these crypto systems? So the NIST curves. Well, the NIST curves are a selection of prime order curves that are in this nice Weierstrass form. And they've been selected. We don't actually exactly know how they were selected. But one approach that you could have, remember I told you the important thing is that the group order needed to be prime, or quasi-prime means like some very small cofactor times the group order. And there's a lot of controversy in the community right now about whether small cofactor is good or bad, right? So a small cofactor can introduce complications in terms of security and extra checks that need to be introduced. But they can also introduce efficiency in terms of what model of a curve you can use, and some group law implementations are faster than others and things like that. So there's actually quite a bit of public debate about that right now. But so going on back to the basic problem, like I said, we need a prime of around 256 bits, so of size like 2 to the 256, and that's because the square root would be then roughly 2 to the 128. So we say this has 128-bit security level, and that's the minimum security level required for government standards. And so we're going to need to generate an elliptic curve with very large prime order, and just using basically kind of the Hasse-Weil theory, you'll know that if you have a curve, we said the number of points is supposed to be p plus 1 plus or minus 2 square root p, or something that's in the interval plus or minus 2 square root p. And in particular, it's p plus 1 minus t, where this t is the trace of Frobenius, which is an endomorphism that acts on an elliptic curve over a finite field. And this t will then be, it will determine, that's the trace of Frobenius. Let's call Frobenius, the endomorphism, call it pi. So then pi will actually end up lying in this quadratic imaginary field because it satisfies a quadratic equation with this discriminant t squared minus 4p. So what ends up happening is that we end up wanting to generate elliptic curves that have p plus 1 minus t points, and where the curve that we'll generate will have a Frobenius that lies in this particular field. This is an imaginary quadratic field. This is negative because of the Hesse-Weil. Okay, so now we can kind of forget about cryptography and, okay, just let me finish my sentence 1 second. We can forget about cryptography and we can switch over to using CM theory to generate these curves. So go ahead.
I'm just wondering, what will be the P for the RSA with the comparable security level?
So again, it will be around 2048 bits, so like 2048 bits. There's some small amount of dispute also how that should be calculated, but it's basically calculated by taking the best known algorithms, which means basically taking number field sieve on the RSA side and taking basically a square root algorithm on this side. Okay, so here's the problem. And this is why I state this as an open problem. So actually, one of the last few times that I was talking with Dick Gross, he stated this problem a little bit more generally and was very excited about it. I still think it's a very interesting problem. Let's say you have a finite field and you want a curve with a certain number of points. Can you give me an algorithm for generating a curve with that number of points? Well, so that's the problem for cryptography that I've stated. So, and now I'll tell you what we actually do in practice. So we have a solution which works pretty well and can handle most of the things that we want to do, especially for elliptic curves. But it's actually a very roundabout solution, and it seems kind of silly that we would have to do this. So what we're actually going to do is we're going to actually construct a curve over a number field, which actually could potentially be a very, very large number field. And then we're going to, or at least in theory, we're constructing it over a number field. And then we're going to reduce it mod p, and we're going to take like a p that splits in this number field, so that we're going to end up getting a curve over a finite field. So it seems like kind of a roundabout way to get to a solution, and there's a problem with our approach. And like I said, I told you it works fairly well in practice, but there's some problems with it, and that is that in order to compute, we're actually not going to compute the curves over a big number field. We're actually going to compute a minimal polynomial for the invariant of the curve, the J invariant in particular. And then we're going to reduce that minimal polynomial modulo p. And so we're doing kind of a roundabout way of getting the curve, because once we've reduced it in mod p, we have a polynomial mod p, which we can factor, take a root, and that's the J invariant of a curve mod p that has the right number of points. So what is the problem with this solution? The Hilbert class polynomial is the minimal polynomial of the J invariant, and its size is roughly d bits. So you can see that in the following way. So it's going to be the Hilbert class polynomial is the minimal polynomial of the J invariant, which generates the Hilbert class field of this field K, Q join square root of D. And it's known that kind of asymptotically, roughly the degree of that polynomial is square root of D. So you've got a polynomial of degree square root of D, and then just from analyzing CM values of the J function, you can see that each one of the coefficients has roughly square root of D bits. In other words, the coefficients are of size like e to the power like square root of D times some power of log. Okay, so just to write down that polynomial would take you d bits. But d is like around the size of p, which is 256. So we're saying this is a polynomial of size like 2 to the power 2 to the power 256. I mean, it's insane. And it takes you in particular d bits just to write it down. So we get around this problem in several ways. So one thing is by taking like if there were a large square factor of this, so say this was like q squared times d prime, then we would do this job just for d prime, where d prime is much smaller than d. So that's one thing we can do. But in general, it's still, you would say it's not a perfect solution to this problem. It's kind of interesting that we have all this beautiful number theory. It provides us a great way to do this, kind of in some cases and in practice, but is kind of unsatisfactory in the sense of solving the problem. So the next thing that I want to talk about, and so most people will know, I'll just talk about this for like 5 more minutes. So most people that have heard me talk before will know that this is my favorite topic, so I could talk about this forever. But so this is the question of generating genus 2 curves for cryptography, which is more difficult than generating elliptic curves for cryptography, because basically you have to do all that CM theory kind of in this higher dimensional case, and there are a lot of more difficult things that come into play. In particular, so I'm not going to run through all the details of it, but it's the same idea. As you say, oh, I want a genus 2 curve with this number of points. That's going to make it so that the zeta function has to be such and such, and that means that I know kind of the isogeny type of this Jacobian. And so now what I really need is to compute an abelian variety, an abelian surface that has CM by a certain quartic CM field. This quartic CM field is defined by some polynomial like this. And so now what I really need to do is to compute like the analog of the Hilbert class polynomial for this quartic CM field. And part of the problem is that the Hilbert class polynomial was nice in the sense that it had integer coefficients, but these other polynomials don't. They have rational coefficients. It makes them much harder to compute. And so you'll end up with things like this, where you take a relatively small field, a quartic CM field with pretty small discriminant, and then you're trying to compute some polynomial. So this is like a degree 8 polynomial. I've only written down a few of the coefficients, and in red down here at the bottom, I've written the denominator. And so when I first started doing these computations long, long ago, and I didn't know what to expect, the real problem, what you face is that you're taking modular functions, you're evaluating them at what are called CM points, and you're evaluating them to very, very, very high precision, thousands of digits of precision. And then you're multiplying the factors together, and you're trying to recognize the coefficients. But you're trying to recognize rational numbers whose denominators are this size. And that kind of stinks. because usually what happens is that you don't recognize anything, it just looks like garbage, and then you don't know what to do other than increase your precision and do it over again. So it was funny because, more than 10 years ago when I was first doing these computations and computer power wasn't quite as good, it would actually take weeks to compute these polynomials, and then you find out that you have garbage. And then so you'd recompute them, and so it's kind of a disappointing process, right? So the nice thing was, when I first started getting a few examples where I could recognize them and got polynomials like this, imagine my surprise when, I don't know for what reason, I factored the denominator. And this is what I got for the factorization of the denominator. So you notice a couple of things about that, right? Very high powers. The high powers are because of the high power of the modular form that appears in the denominator, and very small primes, right, compared to the size of the whole thing. So this is pretty interesting. The thing that was most interesting and kind of most gratifying about this whole area and this whole field is that it turned out to be very connected to some very interesting other results in number theory. So the first thing I thought when I saw this, for some reason or other, it reminded me very much of Gros-Aguier's theorem, where you have these kind of beautiful factorizations into small primes. And so I had this kind of conjecture about that this should be related to Gros and Aguier's theorem, but I didn't exactly know how, and it didn't really make sense. The connection was very, very unclear. And so eventually, after many years of working on this problem, there are a couple of different approaches that were developed. One approach developed jointly with Eyal Goren to give a bound on these primes, and another approach developed by Brunier and Yang using basically kind of Arkelov theory, which predicted actually a factorization formula, which Yang then proved in some special cases, and which I proved in the general case with Bianca Verai for general CM fields. And our proof actually also led us to finally kind of a generalization of Gros and Aguier's theorem. So it's a very nice connection. So I like to tell this story to give the example of a cryptographic problem, which is computing genus 2 curves for cryptography, and then the kind of very practical issue of needing to compute these class polynomials, which is a huge pain, and the fact that now the algorithms are much, much better now that we have an understanding of the denominators. And the theorems which prove what the denominators are purely kind of arithmetic intersection theory theorems, kind of in algebraic geometry, number theory area, which are maybe you could say of independent interest as well, especially in the sense of providing, for example, a generalization of the Gros-Aguier theorem. So that's one example that I like to give of the connection between cryptography and number theory, bringing up new interesting problems. So just to wrap up kind of the comparison between genus 1 and genus 2, what this kind of solution allows us to do, now that we can fairly efficiently compute genus 2 curves using these kind of class polynomials, it allows us to construct genus 2 curves for cryptography which have a number of points which make them attractive, make them kind of safe curves. And in particular, we can construct them over the fields that we want. So we can take fields where we can do very fast arithmetic. We can construct safe curves over those fields. And then we can do implementations of the group law and try to show what the efficiency of the system is. So I like to show this because, so this was a result from 2013, which was joint with some of my co-authors, Voss, Costello, and Hasiel, who are expert implementers in terms of taking various platforms and doing really a fast underlying field arithmetic and fast group arithmetic. And through a combination of a lot of techniques, we were able to show that genus 2 can actually be more efficient than genus 1. So this was kind of an interesting result, because when you look at the two group laws, you think, oh, the genus 2, that would be a lot more complicated to compute. And so this was done through a combination of things. One was, like I said, being able to generate these curves over fields where we could do very fast arithmetic. So the NIST curves, here the genus 1, this is the kind of the standard implementation of the NIST curve, which was the kind of the baseline. And we're able to do a generic genus 2 curve in much fewer cycles. So this is a group operation. This is how many cycles it costs. And then this is a kind of a special family. These are families of curves that have extra endomorphisms. And there you can see that all the records for genus 1 are these assumptions, which is, this category is not as safe in some senses as this category, because these are assuming extra endomorphisms, which can also be used to attack curves. But in that case, the elliptic curve was still faster. But then in a third case, we have this kind of alternate representation of a genus 2 Jacobian, which is a Kummer surface. And you can see we could get very, very fast cryptography or group law over that for that curve. And, but we can't do all protocols with that implementation. So this gives you kind of a picture, and this is a snapshot. So since then, there have been improvements in the elliptic curve group law to make it even faster than that in those kind of special cases. Okay, so my third problem that I wanted to talk about, and I think this is pretty important, and maybe I'll say as an aside, like if you're a graduate student or even a practicing researcher that kind of wants to get into cryptography, a lot of people ask me how to do that, and there's a lot of great books by people like Joe Silverman, and actually there's Silverman, Hofstein, and Pfeiffer. Well, let me see, get it there right. Hofstein, Pfeiffer, and Silverman. There's books by Neil Koblitz. There's all kinds of great books. But the other thing that I thought, oh, I should advertise this. Do you know, around the world, at all the crypto conferences that we have every year, so many of the crypto conferences are running summer schools just 2 or 3 days before their conference. So if you ever really want to go do intensive crypto preparation where you take your algebraic geometry knowledge and all of a sudden learn all about elliptic curve crypto and pairing-based crypto and all these things, you can literally, these are supported actually through the IACR. There was $1 million gift from Paul Coker to the ICR to pay for students to go to these conferences around the world. So there was one last week preceding ECC, and Damien Robert, who's here, was speaking there. And in Latin Crypt in August, we had one before Latin Crypt in Mexico, and Serena Ionica was speaking there. So that's a really good way to get into these things. And pairing-based cryptography is almost always covered in these courses because it's very important, because there's a lot of applications of pairing-based crypto. So what is pairing-based crypto? We have already mentioned that pairings were used to attack the supersingular case of elliptic curves. But then in 2001, several positive applications of pairings were introduced. Bonet and Franklin and Zhu introduced a tripartite Diffie-Hellman. So there are many other applications now. I've only listed a couple, but there are literally thousands of papers on applications of pairings in cryptography, which are very, very important, including attribute-based encryption, public key encryption with keyword search, predicate encryption, even homomorphic encryption in limited senses. So what do we mean by pairings in cryptography? Well, strictly speaking, it just means a bilinear pairing. So you have two groups which may be the same, or they may be like two different subgroups of the same group, as is the case in elliptic curve cryptography. And a pairing just means a bilinear map between the cross product of these two and some other group. And how is it used? And so what the requirements for crypto are that the pairing should be, obviously needs to be easy to compute, but it needs to be hard to invert. So that's why I write pairing inversion as the third problem. I'm going to give you one application of kind of pairing-based cryptography, so you see how it's used and why it kind of needs to be hard to invert. So, or maybe I should say, before I tell you the application of pairing-based cryptography, the main thing that you should be thinking about here is the group of points on an elliptic curve. So think of, like, let's say the M torsion of the elliptic curve and the So 2 pieces of the M torsion and then the multiplicative group of a finite field. So this application is a signature scheme, which is, I think maybe in the interest of time, maybe I won't go into a lot of detail, but the signature scheme, basically you take a secret S, you're going to have some public point P, and you're going to create your public key pair S times P, and this PQ will be your public key pair. And then a signature will be some message, you hash it by taking S times the hash of the message. And the verification, so this can be verified by anyone given your public key. They can just check whether the bilinear pairing of this point Q, your public key, with H of M was the same as the pairing of P with the signature. And that's because in a bilinear pairing, you should be able to move this S from this side over to this side and get the same thing. So that's an application of pairings in cryptography. This is kind of the shortest known signature scheme that we have, which is used in practice in many places. And the main thing that I have kind of highlighted in red up here is that the only known pairings for use in cryptography are these algebraic geometry pairings. So based on the Weil and Tate pairings on elliptic curves and generalizations to Jacobians of hyperelliptic curves. Okay, so unfortunately, I have taken up way too much time with my first 3 problems and do not have time to talk about my 4th one or the other ones. But I would be very happy to take questions about any of these other problems in the break. And I guess the main point that I wanted to get across to you is that this is a very vibrant research area, kind of not within algebraic geometry, but kind of a crossover between algebraic geometry and algorithmic number theory and cryptography, which has lots and lots of open problems to work on. So those of you who are looking for problems, you can find a lot of problems here. So thank you very much.
Are there some more questions?
So I want to go back to the issue of the genus 2 curves, where you were using the CM on the abelian surface, finding that and then finding. So I just want to understand practically, are you, how to say it? Here you're looking for a Jacobian with a certain number of points, right? And then you're picking N1 and N2, and that imposes on you a certain CM. Is it easier? I mean, I guess there's lots of different N1s and N2s that could give you the same N. Is there any way to sort of find a Jacobian with the right number of points that's without sort of finding that N1 and N2?
So in practice, I mean, you're right. So you can, choosing N1 and N2 is specifying the whole zeta function, and you have, for a given number of points for your Jacobian, lots of choices, a certain finite number of choices. And so it's true you can kind of vary your choice and maybe make your field better for computation. But unfortunately, we actually published a paper showing that the best that this approach can be is still really bad, unfortunately, meaning that you cannot come up with a nice kind of polynomial time way of, for an arbitrary group order, getting a field, quartic field K with a discriminant small enough to make it good, unfortunately. And it's just really a counting argument. It kind of counts the number of fields that can have the right property and basically says as you go to infinity, you're gonna lose. That's the bad news. And that's one of the flaws with this approach, right? That this is still this approach of constructing the genus 2 curve over a number field in a sense, as opposed to saying, hey, I have a finite field, now I want a genus 2 curve with this number of points, which is the problem that we don't really have a direct solution to. Does that answer the question?
So if there's an economy of scale between genus 1 and genus 2, why stop at genus 2?
Oh, great question. Thank you for asking that. So maybe about 15 or more years ago, Adelman and Huang proved this very interesting result, which is sub-exponential algorithms for the discrete logarithm problem on very high genus curves. So if you have the genus is roughly like log Q, which you can think of, like you could see we had fairly large fields. I mean, 2 to the whatever power. The log would be, fairly large. If the genus has to be bigger than the log, for very large genus, they have sub-exponential algorithms, meaning like basically L1/2 and kind of conjecturally L1/3 algorithms. And so everybody had this kind of idea, oh, well, if the genus gets too big, the problem, becomes sub-exponential running time to attack it, so we should not really think about high genus. So then the question is, what do you do between like genus 2 and high genus? So there's some known algorithms like for genus 3 and genus 4, which are better than square root algorithms, but they're still exponential algorithms. So for genus 3, which was something which is on my list, there are a bunch of open, interesting problems in genus 3 that some people, even in this audience, are working on. The best known algorithms are like Q to the 4/3 or O twiddle of Q algorithms. So already with genus 3, we're right on the border of whether it's worthwhile to go up to genus 3 because the attacks that are known are better than square root attacks.
Okay, well, let's thank Kristin for that.